Yeah, this is a video about cookie dough, basically the Weissenberg effect, which is visible here. So this rod is spinning, and there's this kind of fluid, and it starts to climb the rod just because the rod is turning or spinning around its own axis. Yeah, I got really curious about non-Newtonian liquids. So, obviously, we can see a spiral shape, which shouldn't come as a surprise to anyone. And I thought I will dive a little bit into that, why it does it. And I found one article which is really fun to read. It's a million miles long, but let's have a look at it. Yeah, it's Hydrodynamic Stability of Newtonian and Non-Newtonian Fluids, 2009. Abstract. I will just read a bit and then I will try to find the one thing I was searching for. This report aims to provide an introduction to the study of linear hydrodynamic stability in both Newtonian and non-Newtonian fluids. We first give some motivations as to why one studies stability of fluid flows in the first place. In Chapter 2, we specify the mathematical tools required for our study. In Chapter 3 and 4, we look at the linear stability of Newtonian and non-Newtonian fluids and compare the relevant results. For our study of non-Newtonian fluids, we will consider shear thinning fluids where viscosities decrease with increasing shear. Our principal hypothesis may be given as follows. The presence of a shear thinning viscosity stabilizes the flow. So, there is this kind of mathematical stuff which I'm not into at all. As you may have noticed, I like pictures. Yeah, this is now the fun part. Introduction. Fluids are all around us. If one glances around, it becomes obvious that a good proportion of the universe is in a fluid state, mostly in gas form, which is plasma. But let's continue. As a study of fluids is highly relevant in our quest to understand more about nature. From a practical point of view, understanding fluid behavior is indispensable. Aircraft and ships travel through fluids. Lubricants for mechanical mechanical Debye fluids. The atmosphere and the weather are governed by fluid dynamics. The list goes on. From a medical point of view, whatever that means, it is extremely interesting, with many open questions that remain to be answered. For example, the existence of a classical solution to the nonlinear and coupled Navier-Stokes equation subject suitable in suitable initial data is very much an open question. Simulation of fluid flow requires extra care because solutions often become ill-defined in finite time. The analysis of the equation rapidly becomes complicated due to the nature of the problem. Understanding the behavior of fluid models has been and will continue to challenge researchers in wide variety of fields such as physics, engineering, geography, oceanography, astrophysics, and of course, mathematics. Yeah, I don't regard mathematics as too much as a science branch. Because it just is a way to prove stuff. So, the term fluid is rather loose, one for our purpose. Here, we shall take a fluid to be a continuous medium which deforms smoothly under stress. We will make precise this concept in the next chapter. Intuitively, we can think of a fluid as anything that flows. Most fluids are sticky to some extent, and we term the degree of stickiness viscosity. Mathematically, it is defined as the ratio between the stress and the strain. The viscosity clearly depends on the fluid under consideration, but a natural question to ask is whether the fluid's viscosity depends on the factors such as time, temperature, and the force applied to the fluid. Some fluids, such as water, have viscosity which is independent of stress or time. This was the assumption Newton made when he first proposed a model for fluid studies. We call such fluids Newtonian, where the relation between the stress and the strain is linear, i.e., the viscosity is constant. It soon became clear from physical observations that some fluids exhibit variable viscosity. In other words, the stress-strain relation is nonlinear, and we call these non-Newtonian fluids. Some examples of these are shear thinning fluids, so substances and mixtures such as oil-based paint, toothpaste, mayonnaise, and quicksand are fairly viscous at first glance, almost gel-like. Under stress, they seem to flow more easily, as observed by stirring a pot of paint or stepping on the quicksand. Fluids of this type have decreasing viscosity under increasing stress. Sometimes they are called pseudoplastics, and in fact, the majority of non-Newtonian fluids are shear thickening. Shear thickening fluids, custard and corn starch mixtures hardens under stress, in effect becoming more viscous. One well known experiment involves people running across pools of custard without sinking into it, thanks to the fluid possessing a more solid like structure under stress. Fluids of this type, which have increasing viscosity under increasing stress, are also known as dilatant fluids. Food products such as mayonnaise and biological fluids such as synovial fluid are thixotropic. They decrease in viscosity the longer they are exposed to stress. Mud exhibits this property, and earthquake zones liquefaction occurs, causing landslides. The structural weakening is due to forces acting on the substance. Yeah, you can read the whole stuff. That's really a long article. And of course, we have the Newtonian fluid, which is behaving perfectly constant whatever happens, such as Newtonian science does. Uniformitarianism. You know, let's go back to the video. So, as we are watching this one here, I was thinking about something. Yeah. you know, this is spinning. This rod is spinning. There's no grip on it whatsoever. We had recently those tornadoes at the volcano, which is basically the same thing, like this rod. This just energy which is spinning, and now it here in this case it just happens to be this metal rod here. So it starts to, if we would watch from above, this would be the rod which is spinning into one direction. There's stuff attaching to it which also starts to spin in one direction. But there could be this kind of, let's try to paint it a little bit different with different colors. We get the first layer which gets attached to the rod. Let's draw probably a nice circle. And then we get the next layer, which might be really much more thin than the first one. Then we get the next one. Which is probably less spinning than those. And this red circle, what I was painting before, this could even spin in the opposite direction. So this is going the same way like the rod. This is the red one to the other side, and this is again going to that side. Like if you would watch here from on top into that thing. So there could be a possibility that if you would really close watch at these outer layers, that they would probably somehow would move downwards because of gravity, for example. I wanted to show you another video. This is about the Weissenberg effect. That's from Switzerland, Department of Materials. And I was just talking about this tornado thing. That's the tornado, which is sucking stuff upwards, but there's also stuff going downwards, like a Bergland current. Layers in layers which spin to opposite directions. And I try to explain somehow that for me it seems this kind of volcanic tornado, it makes just somehow a connection from the ash. If that's the tornado, if that's the volcano, that's the ash cloud, which is electrically charged. One indicator is the heat. Okay. And there's lava underneath the ground, wherever it is, which is also electrically charged. And in order to make a full circuit, there can be established this kind of connection, which is a tornado, which connects the energy from here to the energy here below. And keeping that in mind, watch the next video and watch how it works or how it reacts. That's again the same thing. Keep in mind that's just a straight rod. There's no profile, no spiral or whatever. There's just probably a drop of this red fluid dropped into that. They stick the rod in it and it just starts to spin into one direction. Check it out. Like if this would be the tornado, the connection to the above, look what is happening here below. If that's the surface, what we can see from where the tornado starts. This you can see, of course, in the video from the volcano. Imagine this red stuff here on the bottom would be somehow energy. It gets distributed into the ground. It goes down. And at the same way, we have this little uprise here on the top. So if this red stuff would be another viscosity, it would rise much more up here, this rod, just because it's spinning. Yeah, I will leave it here. You can read the article, watch the videos, and make up your own mind. But if you apply this kind of spinning, which is a force which can be measured also electrically, you create this kind of, how to put it, energy flow, which is, after all, electric. So those tornadoes and the cookie dough and the mess you probably get when you make cookies soon because it's Christmas, they're all related together, I guess. Probably the why the stuff is rising up this rod here, they are maybe forming like those molecules inside. Maybe I use another color, nobody sees what I'm drawing. If this would be molecules or something, or atoms, because you get this implement of the spinning energy, they probably will align and they will form a daisy chain, which will provide then somehow its own energy field. I leave it here. This was something pulled out of the hat. Thanks. Bye.